charge exchange in general in ion-atom collisions, and in particular in collisions of hydrogen and helium plus. And in particular also hydrogen in excited states, which might be a bit unusual, but it's very interesting, in particular when you're in the context of spin-dependent effects. So here's the outline of my talk. We'll start with a quick introduction, and then I will describe the method that we used, some of initial calculations, and the calculation of charge transfer per sections. So I guess you will not learn much from my introduction because I'm sure you all know what I'm going to say here. But there are a few important applications of charge transfer in the context of astrophysics and plasma physics. A lot of people have talked about these applications during this workshop. So X-rays in the solar system, the soft X-ray background, supernova remnants, the analyzed regions, etc. There is a lot of measurements available to describe these processes. And so I'm not going to focus on that. I'd just like to point out that this usually requires cross-sections for highly charged ions with hydrogen and helium in the range of energy of about a keV range. So that's one application. Another one is the modeling of some astrophysical environments. For example, charge transfer can be important in the context of trying to understand the chemistry of the early universe. This is mostly charge transfer involving hydrogen and helium or lithium, but also for example, if you're trying to model the composition of cometary atmospheres. For example, now, as you know, there's this Rosetta mission orbiting the 67P comet, and they can measure the composition of various elements using mass spectrometry. And so to understand the observations, you might need to have a model describing the abundance of various atoms and molecules, and charge transfer is important in that context too. In this case, it's mostly H++ O, OH, H2O, these kind of molecules. So it's, of course, when you go into polyatomic molecules, it's very hard to treat theoretically, so it relies more on experiments. But it's very important to have accurate values, especially since when you look at the models that they use, usually have a weight constant at a single temperature, and so they don't use cross section. There's no dependency in the temperature, so it's also important to consider this. And the third application is in the context of laboratory plasma, in particular with the fusion processes and the ITER reactor that is being built in France right now. And so as you know, you have this tokamak, donut shape, containing plasma, and it's very hard to extract useful information from that plasma. So what you can do is use the presence of so-called impurities in the plasma. There are two kinds of impurities. You have these intrinsic impurities, such as carbon, silicium, etc., which come from the wall of the tokamak. Because the plasma hits the wall, it brings back impurities in the plasma, which is a big problem, because if you use the plasma, you lose power, etc. But you can also use them as a diagnostic tool, mainly through line emission. There's another type of impurity, which is the extrinsic impurity, which basically means that you inject impurities in order to, for example, heat the plasma, and you can also use line emission to extract useful information from that. Now, a lot of work has been done in this context on using emission lines of helium-like ions, and there are several reasons for that. One of them is that the spectrum of these helium-like ions is simple enough that you can actually compute it very accurately, but it's also complicated enough so that you can get useful information from it, such as ion temperature or electronic temperature, etc. Here you can see an example for helium-like argon, and you can see a very nice comparison between theory and experiment. Now, I said they usually like to use helium-like ions. Well, you can also simply use helium, because there's a lot of helium in your plasma. It's produced during the reaction, okay, and it's not useful in the plasma, so you want to extract it, and you can actually use the helium also as a diagnostic tool. And so if you try to do that, you have to include a lot of processes that can influence the population of the various electronic levels of helium. So you have to consider a bunch of processes, and one of them is charge transfer. In particular, this charge transfer between helium plus and hydrogen, which gives you helium in an excited state and a proton. And the reason you have to consider excited states here, and not only the ground state, is because even though the population of excited states of hydrogen might be relatively small, you expect the cross-section to scale very badly with the principal quantum number as n to the power 4. It might not be as bad as n to the 4, but still that compensates the low population of this excited state. And so what we did was to look at this fraction and compute the cross-section in this energy range, so from 0.1 eV to 1 to 10 keV, which is typical to the so-called divertor conditions, so the edge of the plasma. And also the reason is that there were no existing fully quantum mechanical calculations or experimental data on this system. But it can also be useful for astrophysical application. Now, so the goal is to compute the cross-sections, as you know. And so we've heard during the past 2 days about various methods that you can use to compute the cross-sections. And I divided them into 2 categories. The first one is so-called molecular methods. So that means that when you have a collision between an ion and an atom, you consider that they form a quasi-molecular ion or quasi-molecule, and you can treat the problem from that point of view. And so there are a few methods that use the molecular approach. The best one is a so-called coupled channel, which is, well, it should be varied at any energy, but it gets very computationally expensive. So you usually only use it at low energy. And then you can use either time-independent methods or time-dependent methods. This has not been talked about in this workshop, so I thought I would just mention it. These 2 methods are completely equivalent. It's just a choice of solving either the time-independent Schrödinger equation or time-dependent Schrödinger equation. And they each have their advantages and drawbacks. For example, the time-independent method is very nice for small systems, but for polyatomic molecules it becomes very, very complicated, whereas the wave packet method is easier to use for larger systems. On the other hand, when you go to very low energy, so like 0.01 eV, so I think for most of you here that's very, very low energy, but I mean, you can go down to much, much lower, of course. The wave packet method completely breaks down, whereas the time-independent method works very well. And so these are 2 different types of problem mathematically, but they're completely equivalent. And one of the nice advantages of time-dependent methods is that you can include easily time-dependent perturbations, such as external fields. For example, it's not very much of a concern in this case, but it's still nice to be able to do that. You also have aconal methods, which are semi-classical methods, so you still use the potential energy curves, but the motion of the nuclei is treated classically. These are valid in this type of energy range. It's approximate, depends on the system. And these are much, much faster, of course, to use. And then you have these Landau-Zehner, Rosen-Zehner methods, which use properties of the potential energy curves to compute the sections easily. So these methods are all based on the separation of the electronic and nuclear motion, so what's called the Born-Oppenheimer approximation. So I guess you'll know this also. You divide your Hamiltonian in 2 parts, and so in the first step you solve the electronic motion, gives you access to the potential energy curves, couplings, etc. And then in the second step you compute the cross-section or wave coefficient, so whatever you like. And so you can already understand the usefulness of trying to find scaling laws to describe cross-section, because this is a very complicated problem, and doing it for a single system takes a long time, so it would be useful to be able to to have general information on these processes. And then you have a second type of methods which are based on which I call the atomic methods. So you also heard about those methods during the previous days. There is also an atonal atomic method, continuous distributed wave method, Monte Carlo methods, and they're all valid in different energy range. Usually it's at higher energy. And here I will talk mainly about really molecular methods. So I will focus on two electron systems because that's where you can find this triplet to singlet ratio that Vasily likes so much.
No, I hate it.
And of course, I will restrict myself to ion atom collisions because it's complicated enough as it is. So here are a few examples that you know of two electron systems. Usually collisions of hydrogen-like ion with hydrogen in the ground state, producing any excited state of helium-like ions. You can also have effective two electron systems. So you have a closed shell plus an electron colliding with hydrogen 1s. It's basically the same problem. And a very general observation is that since the ionization potential of helium-like ions is larger than that of hydrogen, the entrance channel here is always above the product channel. Okay. So here is a typical example. It's for NH4+, corresponding to this collision between N4+ and H. And you see the entrance channel here, N4+, 1s plus H1s, and then you have all the product channels that are located below. Okay, so you will enter here, there is some avoided crossing, so you know that you have a certain probability to go to the lower states, and you can compute the cross-section to win in any of those states. And the particularity of this type of collision is that in the entrance channel you have an ion colliding with an atom, so you have a potential proportional asymptotically goes as 1 over r to the 4, and the product channels are ion plus ion, so it's a Coulomb potential. Okay, so you know you're going to have some crossings at some point.
Jerome, this is the reason why you're guaranteed that all other product states are below.
Yeah.
It's an exothermic problem.
Right. Yeah. And so the question is the ratio of cross-section for triplet relative to singlet state, because you can form either triplet or singlet state during the collision. Is it statistical? So is it 3 to 1? And as I'm sure you know, the answer will be no. Here is an example again for this this N4 plus H collision that I mentioned, with some experimental values here and here. In red you have the statistical values, 3, and some calculations. And you can see in general that it's clearly not 3, it's between 1 and 5, something like that. But it's not obvious to predict the value. And from a computational point of view, so from my point of view, the question can be transformed into, can we limit ourselves to calculating either singlet or triplet states, because it's twice as much work to do it for both spin symmetry reports. Now, what about the collision I'm interested in? So helium plus H. Well, it's not exactly representative of what I mentioned, and there are several reasons. The first is that, so in this case, you had a bunch of excited states between the entrance channel and the exit channel. In the case of this collision, if hydrogen is in the ground state, you have no excited states between them, so it's kind of very easy problem. But of course, if you go into excited states, it's not that obvious anymore. And the other difference is that here you have an ion and an atom, so that's the same case as previously, but at the end you also have an atom and an ion. So it's the same type of potential, 1 over r to the 4, instead of having a Coulomb potential. So it's a pretty different.
May I ask a question at this point?
Yeah.
How important is it for you to be thinking it from going from left to right, as opposed to going from right to left?
It's not.
Okay, it's exactly the same.
Yeah.
Because that's, in my mind, I'm just thinking this is proton scattering on helium.
Sure.
I have to treat helium with the spins as they are, and there's just one electron transfer, and that's it. So, again, from my perspective, it's like a positron scattering in helium, which is what we've done, and you have charge transfer to form positronium.
Right.
So, it's
Yeah,
that same process.
do it in both
directions, okay.
Completely equivalent.
Yeah.
Yeah. The question: what Mother Nature doing? Usually, it's doing differently in this direction. Yeah. You have a helium flux. Yeah.
Because our stuff is time independent.
In comet,
Right.
no, I understand. Yeah, in comet usually this is important because this process creates the neutral wind. Yeah, solar wind penetrates the cometary atmosphere. Helium usually double charge, capture 2 electrons or 1 electron, then capture electron again. And after comet, it's a strange. They found now detected. Yeah, not only energetic neutrals, kill electron volt neutrals, yeah, but also negative ions. Yeah, it's another question, but they have a negative H minus. Yeah, as a flux.
I guess the thing I would emphasize, I would not think of treating helium any other way than the way you've written it down. It's a 2-electron system. It has spin, no choice in the matter. Okay.
Yeah. Okay. So I think I will go through this very quickly. It's just a reminder of the Born-Oppenheimer approximation. So how you solve the electronic motion, and when you do that, you get your potential energy curves here, okay, and your electronic wave function. You can use them to integrate your Hamiltonian over the electronic wave function, and you find this type of Hamiltonian. So you have 3 different types of terms. A completely diagonal term here, which contains just the kinetic term, centrifugal term, and your potential energy curves. The second term, which contains the so-called non-adiabatic radial couplings, which connect states of the same spatial symmetry, and then the third term connects states which differ by 1 unit of lambda, so sigma connects sigma to pi states, pi to delta states, etc., which is called the rotational couplings. Okay, and so of course you have to calculate those in addition to your potential energy curves to be able to treat the problem accurately. And if you want, you can also include other corrections, such as adiabatic corrections if you're going to very low energy, spin orbit, if you consider heavy atoms, etc. Okay. So as I told you, I'm interested in this collision for involving excited states. So ideally, you would like to go to as high as you can. In this case, we limited ourselves to values of n between 1 and 3 because it becomes very hard very quickly. And we used standard methods of quantum chemistry, so the Monroe package with large basis sets and very accurate methods. And so, just to give you an example, here's the number of states that you have to consider. So for n equal 1, you have 3 states. For n equal 2, you have 6 states for singlet symmetry and 6 for triplet. For n equal 3, you have 6 plus 4 plus 2, so it becomes very complicated very easily. And so we will just stop at n equal 3. So here is an example of the potential energy curves that you get. This is for singlet sigma states. And you can see the ground state is helium plus H plus, then you have helium plus 1s, H1s, and then you have a bunch of different states that dissociate either into excited helium plus a proton or helium plus excited hydrogen. And what you can see is that the 2 types of curves alternate along the spectrum. So you know the possibility of having charge transfer processes is very high because you have a lot of avoided crossings everywhere, especially in the excited states. So if you zoom on that part, this is what it looks like. And I put all the dissociating channels here for as the potential energy curves. And you can already see that it's going to be quite a complicated issue to extract general trends from the charge transfer process. Okay, and one of the difference between singlet and triplet states, which is useful to try to understand what's going on after from the ratio of triplet to singlet cross sections, is to look at the order of the states here. And on Monday it was mentioned that for states of helium, the order of states is not the same for singlet and triplet states. For example, here for singlet state you have helium 1s3s, 1s3d, 1s3p. Whereas if you look at triplet states, so this is the same figure but for triplet states, you have 1s3s, then 1s3p, then 1s3d. So the order is not the same, and in addition, you see that of course the shape of the curves is a bit different for both symmetries. So you already know that it's going to be quite complicated to extract general trends. Okay, so you know that when you have those avoided crossings, you will have radial couplings. This is how the charge transfer occurs. And you also calculate the rotational couplings. This is just show an example. It's not very interesting in this case. Okay, so now
let me ask you a question about this matrix element.
Yeah.
As your rotational coupling certainly not vanish to infinity. Could you return back?
Oh, yes, sir.
Yeah, if you look at the matrix element here, it goes to not to zero to infinity.
Yeah.
You should correct this also when you project on atomic state. Yeah?
Right.
Is it kind of technically how it works technically? What you do?
Well, you have to divide them by r squared. So then they do it. Okay, here I put the r squared, but it's not included
No.
here. So
Rotational matrix
zero,
element not vanish to infinity. It's clear. Yeah. The question, usually you do additional operation like the projection on atomic state, which cuts this artificial interaction. I think about it, because it's already divided with r squared.
No, it's not. That's a mistake. It's not.
It's a mistake.
Yeah, sorry.
You think?
Yeah, I'm sure. I remember quite clearly.
Yeah. Because the angle stopped. You don't axis not rotate. On the large distance.
I mean, he's just calculated the matrix out, is what he's showing.
Yeah. It's only matrix. Okay.
Okay, so I mentioned the methods at the beginning. So we used both time-independent methods. So I won't come back to that because it's been explained previously. I would just like to mention the time-dependent method. So again, it's completely equivalent. I like it because I think it's quite intuitive, but in the context of ion atom collisions, I have to say it's not particularly advantageous to use compared to time-independent methods. And so the idea is that you consider the initial state that you're in, and you use a Gaussian wave packet to put it on the potential energy curve, and then you propagate it in time over the potential energy curve. So a schematic view of this is like this. So you start from this state, your potential wave packet. Once it reaches the crossing region, part of the wave packet which will switch states, then everything comes back to the asymptotic region, and you can extract the cross-section from this information. Okay. And then we use the second method, which is based on an equinal approach, which is semi-classical and which is very at higher energy, so it's much faster to use. But you should be careful that the result of the two methods are the same, that they overlap on some energy range. And then at very high energy, I won't mention this, but we also use the semi-classical atomic method, but I won't really talk about this energy range here. Okay, so here is an example of it's not the reaction I mentioned previously, but it's the opposite one, so proton plus helium. And so you can see that for that system there are a lot of experimental data over a very large energy range. And so these were 3 types of calculations performed previously, not by me. And you can see that basically in each energy range you have a method that describes quite well what's going on. But it's not completely clear how they overlap, okay? Here it seems like they overlap well, but the slope of the cross-section is not the same, okay? And here, the atomic method here doesn't recover the shoulder of the cross-section here very well. So it's not completely clear how you can combine all the different methods, but it's quite important if you want to know the cross-section exactly at that point. You have to be careful. And so, using the 3 methods that I just mentioned, we were able to do exactly that, and so to provide a new cross-section for this process over the whole energy range, which is completely continuous and so can be used, for example, in plasma physics or astrophysics. Now for the reaction that I wanted to talk about, so hydrogen in excited states plus helium plus. Here is an example of state-to-state cross-section. So you start from 2s, hydrogen 2s, and you end up in helium 2p, 1s 2p. You have several things on this graph. So it's cross-section, it's a function of energy. And then you have, in black, here, you have the cross-section calculated using quantum mechanical methods. And in red, the same cross-section but using semi-classical methods. So you can see that they overlap completely around this range. So that means that you're doing things correctly. And the points are the same calculation but with rotational couplings. And in blue, the same thing but semi-classical. So this confirms that the approach is valid and you have really a nice overlap between the different methods. Now you can look at other cross-sections. For example, in initial state 2p, you have to sum over the different values of lambda, of course. And then for final states, just 1s 2s or 1s 2p, you can see different things. You have the singlet in black and the triplet cross-section in red. And you can see that, for example, for this process, the cross-sections are very different, especially at low energy. But the low energy part of the cross-section depends completely on the details of the potential energy curves. So it's, to understand what's going on at low energy, you really need to know the potentials accurately. But even at high energy, it doesn't seem like they're comparable. For this one, they actually go through more or less the same value. So it really depends on your final state. Here's what happens when you sum over all the final states. So you suppose that you start from hydrogen in some NL state, and you sum over all the final charge transfer states. So you have cross-section for 2s, 2p, 3s, 3p, 3d. So you can see a few things. The first is that, as expected, the cross-section increases with the value of n, and it also increases with the value of L. So the cross-section for 3p is larger than for 3d, 3d is even larger. And again, what happens at low energy can only be understood if you look at the potential energy curves. For example, these two here, 2s and 3s, they have a threshold, so that means that you need a certain energy to reach an avoided crossing, so that there's no way to understand this before doing the actual initial calculation. So what happens finally to this triplet to singlet ratio? Here is what happens for n equal 2. So you start with hydrogen 2s or 2p. You have the statistical value here in blue. And so you can see that at low energy, again, there's no way to really understand what's going on except by computing the potentials accurately. At high energy, it seems to go towards more or less a statistical value. So here it's between 2 and 3. Here it's between 1 and 3. So it's not very statistical. The values are close, if you can call them close, but it's definitely not statistical. And then for even more excited states, for n equal 3, 3s, 3p, 3d. For 3s, there's a region here where it looks like it's statistical, but then at higher energy, it goes really to high values, higher than 10. For 3p, this is a linear scale, so it's much better, of course. It's kind of close to 3, but again, at high energy, it goes down. And for 3d, it actually goes to a value close to 3. So in general, it's very hard to predict the value of this ratio without doing the actual calculation, which I guess is very bad news for everyone, because it means you have to really do the calculations. At least for this type of system, when you have a lot of molecular channels that you have to consider and that are completely mixed. So, to summarize, I hope I showed you that various methods can be applied and they are complementary, and you can really, you just have to be careful that they give the same result over some energy range, but then once that is proven, you can really use them to get the cross-section over a wide energy range. I didn't mention this during the talk, but in this case at least, it's very important to consider molecular channels that are above the initial state, which is not always done. We observed the trends in principal quantum number and orbital quantum number, but no real scaling law, in particular because it depends a lot on the energy of the collision. And regarding the triplet to singlet ratio, while at low energy, like everything else, it depends on the details of the potentials. At high energy, it looks like it's getting close to 3, but there are large deviations still. And what I mean by high energy, as you saw, was about 1 keV. I didn't go higher here. And so in general, unfortunately, it looks like it requires accurate calculations. So I would just like to acknowledge the contribution of a few people here. Nathalie Bach in Brussels, Michel Duster-Lecomte for all that concerns the wave packet approach, Sergei Levchenko from Russia, Vasily, who pointed out to me the importance of this triplet to singlet ratio, and Alex Delgado also. He didn't really work with me on that particular subject, but I would just like to say a few words because I was a postdoc here at ITAMP for 2 years, between 2010 until 2012. And the first year I was here, I had gotten a fellowship from Belgium, and I wanted to come to ITAMP and in particular to work with him, and he was actually very enthusiastic about that, so I was very happy too. And I remember the first time I got here, so my first day, he wanted to meet with me and talk about what project we might do together, and I was very intimidated to meet him, of course, and actually very scared also. But it was very nice. He welcomed me with open arms. We talked in his office for quite a while. I took a lot of notes, and then it took me a few days or a few weeks to actually understand all that he told me about, because he obviously knew everything a lot more than I did. And after that, we met once in a while in his office. I would always take a lot of notes and then take a few hours to really try to understand what he wanted to do. And after the end of that first year, I wasn't sure what I was going to do, and then he offered me to stay. He told me he could fund my position for up to a year. So of course I accepted gratefully. And then that second year we didn't interact as much because at some point we had some health issues. But despite that, he would still come almost every day to work because that's what he wanted to do. And as an illustration, this picture that was taken 3 years ago, right about the time when I left, you can see some familiar faces. Vasily is there, Hussein, Jim, and Alex was there, still going strong. And so I would just like to thank him for welcoming me to ITAMP and giving me the opportunity to work here for 2 years. Thank you.
Thank you very much. Please, your question, please. Yeah.
I wonder if there is a clear experimental evidence of importance for charge exchange from excited states of hydrogen. Certainly this process would depend on the population of those states, and in astrophysical plasmas they're probably negligible. Probably less so in fusion plasmas. In the diverter region you may have some population there, but then because you have competing processes, you mentioned charge exchange versus excitation by electrons.
Right.
So is there any evidence that this process is important?
Well, some people made models of helium population, the population of the various electronic states of helium in the plasma, including some of these processes, combination, excitation, etc. And their conclusion was that charge transfer was actually very important, but they couldn't include it explicitly because they didn't know the cross sections. But the conclusion seemed to be that it could affect.
You're talking about charge transfer from excited states.
Right. Yeah. Isn't
So
that-
it's still like evolution, it's just a theory.
No, it's been observed. For example, an argon, human like argon, has been seen to come from hydrogenic argon from excited states. The Alcatraz tokamak was a PRL about 30 years ago. And it's been known ever since, and so it does get included
From excited states of
of
hydrogen.
hydrogen.
Okay, so
Okay, please.
Did you show the triplet singlet ratio for n equals 2 states? Yeah, I noticed this one, and for n equals 3, it looks like they're going to 3 for the largest L.
Right.
Maybe, so
yeah.
I don't know, because it's a classical state, maybe there's some trend. So the other two, 3s and 3p, they're
Yeah.
converging.
That's true. Could
I don't
be.
know.
Yeah,
Doesn't
actually,
know.
the problem is also that you don't have a large sample to
Right.
to extract information, of course. It would be useful to have the same for n equal 4, but then it's just
Too much.
so unrelated to the other one.
Please.
From the viewpoint of somebody who doesn't do these kind of calculations, but whenever I see a curve like that one on the right, where it's very clear that at some places it's sort of dinking up at the single data point, do you think that the little small jinks, are those possibly numerical instabilities or other issues, or are those real features in in this curve?
You mean here?
Yeah.
Well, so the first thing is that there are two curves superimposed.
Mhm.
The first one is the quantum linear calculation, and the other one is semi-classical. So that's the first thing. But then, of course, you have these small resonances. And in this case, I really think they are.
You could resolve those in...
Yeah. The reason you have those also is, I mean, depends on the process, but you usually have some resonances. And then here it's summed over a lot of final states. And so
those will-
there's like 10 it's a sum over like 10 different cross sections. So when you sum everything, you can have really detailed stuff going on.
Okay.
Okay, thank you very much.